Hello, my name is Dr. Michael Okereke. I'm making another video in this series of getting you started with modeling series, especially finite element modeling. And in this particular video is dealing with nano-composites, and we'll be using ABAQUS, which is a commercial finite element software, to do this. So I'm going to show you a bit of the slides that I've prepared ahead of this video. So what you see here is something I've taken from this paper, which is published a while ago. It's Institute Fabrication of Titanium Carbide, particulate locally reinforced aluminum matrix composites for self-propagating reaction during casting. And this is a micrograph of this kind of material showing different volume fractions. So this is 20%, 30%, and 40%. So it has titanium carbide with MMA, metallic composites, so with an aluminium alloy. And we're going to model this problem using ABAQUS. So if we go ahead and look more closely, so what I've called silicon carbide should actually be titanium carbide, and I've represented it here as these little circles, okay, which is kind of an approximate representation of that. And the regions that are in black is currently in this sketch in white. So I've just picked a few of these circles to represent the carbide, and the space within which I'm modeling is a 10 by 10 micron space, 10 by 10 micron, and the particle size is about it's a radius of 1 micron, and there are basically six particles in this inclusion, which gives us an average of a volume fraction of about 18.8%, about 19%, approximately 20. Of course, we can adjust the sizes so that we can get the right volume fraction, but this is just for demonstration purposes. So it's an aluminum titanium carbide or aluminum silicon carbide, whichever one you want to use. In this case, I want to model with aluminum silicon carbide. So the materials inclusions are the components are silicon carbide and aluminum alloy. So the Young's modulus of silicon carbide is 140 megapascal, that of aluminum is 70 megapascal, and these are their approximate volume fraction. 20% or 18%, depending on what you want to use. So this particular design will be 18.85%. So let's move on to ABAQUS, which is really what we want to use to do this. So if you load ABAQUS, go into the environment. So I'm going to show you what you basically need to do. First, you need to create the two parts. So if you double click parts, so it would open up the window. So let me just minimize this magnifier. So if you double click that part, then you try and filling into that. So I'm going to create the first part, which I'm going to call basically the alum matrix, something like that. I'm going to do it in 2D form. It's a deformable material, a shell structure, and this approximate size, you have to decide on how you're going to go about it. I usually would take 4 times the biggest size of the structure. So our size is 10 by 10. So this I'll probably make about 40 about the longest size. So that gives you this environment, and then we can then go here, select, and then maybe you could start from this 0 point, and then you obviously want to make it 10 by 10. So I will make 10 on the x-axis, 10 on the y-axis. So if you click on this button, it will put everything in view. So this is basically the geometry of the sample that we have created. So I'm going to click done at the base. So that creates, if I go back to my parts, so I will see that the aluminum has been created. So the next thing I need to create now is the silicon carbide particle. Okay, silicon carbide particles. So again, so let me just have a look. So if we go back again, I think I'll just cancel that. So if you go to the base here, you can deactivate that. Because I want to cancel that operation. I want to walk you through that process again. So if you go close again, double click on parts. So it gives you this window, so you call it silicon carbide particle. Okay, so it's 2D shell, everything is inherited like the previous one. so that's fine. So what we're going to now do is to create the circle. So I'm going to create, so I'll basically click that. My circle will be at the origin. I'll start first by saying, okay, I want the circle to be at the origin. So I'll go to the base here and type the origin 0, 0. Okay, and how big do I want the circle to be? Okay, click there. So it doesn't really matter what size of circle you select, but the key thing is that you have to dimension the circle. So if we dimension the circle, so go back here, select the circle. So we know that we want the circle to be of size 1. So already in this case is of radius 1. Yes, so that's what we want the circle to be, of a radius 1. So now we have the structure in place. So we now need to create duplicates of the structure, so that it can fill into the spaces that we want. So the easiest way to do this, so let's see if we can delete this dimensioning thing. So I can select and click delete. So the easiest way to do this is to use this button which says translate. Okay, so if you click the translate button, okay, select the sample, but before you select that, I want to create a copy. So select the sample there, click done. Where is the start position? Here. So I'll start position. Where do I want to move it to? Okay, so I'll go back to my table. So I want to move it. This is the positions that I've already together, 5.5 and 4.3. So 5.5, 4.3, which are the X and Y column. This is something you randomly choose. I use the software to help me generate these random coordinate positions. But you can always just randomly create these positions yourself. So that's first one. So I'll do the same. I'll click on that point again, which is here. So if you click on there again, okay, we're using this as a template. So, but obviously we want to create a copy of that. So at the base, you create copy. We select that particle again, done. So where are we starting from? The origin. Okay, so let's go back. So we want to start at the origin 0, 0, and then we want to move it to 6.4, 6.5, 6.4, 6.5. So if you zoom here, you'll see 6.4, 6.5. Okay, so we enter. So that goes into the second position. So we'll do the same. Go back here, click copy at the base, copy this material. We'll pick up where it is, done. Starting at 0, 0, which is the original position, to where we want to go now, which is 9.5, 2.1, 9.5, okay, 2.1, okay, 2.5, it doesn't really matter. So so we can do the same again. So copy, select the sample that we want, done. From there to 7.1, 2.4, 7.1, 2.4. Okay, so okay, now that we've made those adjustments and we've created all the particles, it doesn't look like it. The final point I wanted to make is that this reference particle that we are using right at the beginning, we need to delete that. So we delete that particle, and everything is all done for. So we go 1, 2, 3, 4, 5, 6. Essentially 6. These are extreme particles, so we'll come back to that. So now I click OK, done. So everything is done. So what you will find here is that we've got the matrix component. We've also got the particle component. Now let's quickly now look at the materials. So we want to use the two materials, so we'll click on materials here so that we can create the material. So aluminium alloy. So what is its elastic properties we want to create? So the elastic properties here, Young's modulus, we found that to be 70 e to power 9, 70 gigapascal. Let's use a common Poisson ratio of 0.33 for that. So we'll do the same. We'll go back there, we'll click on materials, and that should give us another window to create. So I'll click on that materials. So this is silicon carbide. So let's call that. And we found that its Young's modulus, if we use the elastic option, its Young's modulus is 140 e to the power 9, 0.33, probably the same Poisson ratio. So we've got that. Then we need to create sections for those materials. So double click, so alum section, so I call it aluminum section, accept all those defaults. So that's aluminum alloy. Another section for silicon carbide section, so SIC section. So we select that as silicon carbide. And then the next thing is we need to create the section assignments. So we need to relate the materials that we're seeing here to these sections that we've created. So how do we do that? So we double click on this, okay, under the aluminum section. So I found the material, so I'll select it, click done. Now I'm going to assign it to the section I've created. So this is silicon carbide. So this is how ABAQUS understands that this particular geometry has to be modeled as an aluminum material. So we'll go over to the metric section. So double click on that. So it gives me the window. I basically draw a box, select everything on that, and then I'll go in here and select the silicon carbide that we wanted to work with. So we'll click that. Okay, so those are all done. Now we need to bring those two different particles because at the moment they are sitting in different places. So we'll jump to the assembly portion. So if you open up this tree, there is an instances, you double click on instances. So it brings up a window that gives you the two instances. So you press down Control Shift or Shift, press down Shift, select both instances. If you look inside the main window, it shows you everything. So we'll accept that. So this is, again, now it's showing us the sort of geometry that we'll expect, with this being the metrics and this being the fiber. So we've got them all represented. So you can go to the top end here and look at the instances, different instance types. So one instance, so let's look for materials. So different materials. So it shows different materials, shows the fiber in place the way they are. So at least we could see the region and the fibers being all looking all different. Now, but we need to bring them together. ABAQUS need to see these two things as one material. So what we're going to do is that we're going to go back into the instances module, the assembly module, select both of them, okay? Select both of them and merge them. So there is this button here called merge/cut instances. So we'll select that. So it gives us a window. So now I'm going to call this alum silicon carbide composite, or just call it alum silicon carbide. So I want to merge. So if you look what we have here, I want to merge them based on their geometry, not on the mesh. We haven't meshed them. I will suppress the original instance and retain the intersections so that I could see where the differences are. So then continue. Now it says at the big select the instances to merge. Okay, so we just need to draw a big box around everything. Okay, so yeah, so it's merged it. How do we know that it has merged it? So we need to go back into the part section. So if you go to the part section of the model, what you will find here is there's a new entry called the alum SIC. If we double click on that, so it brings it into as a part, showing you that it has been made. It has been merged. So it's been merged. So we could look at the section assignments. So what we have here is everything is being treated as, so we have to reselect this. So if I select the region again, continue, select just, okay, so I'm going to select here, selecting the viewport. So this is just the aluminum alone. Okay, fine. So the same thing, now we've selected that. So we're going to reselect everything now and press down Control and select the aluminum. So it deselects the aluminum, leaving only the fiber in place. So if you double click section, dismiss, no. So we need to section assignment. So what regions do you want to select? Everything here deselect by pressing down Control Done. So now I have the silicon material. So then I can change the different material type just to show how different they are. Okay, so now I know that things are properly selected. The final thing we need to do as part of creating this model is to trim off these boundary fibers, you know, the boundary particles, because they are not part of the component. They were created just to preserve the volume fraction, so that this tiny bit that's remaining here completes this cycle. So this was an automatic thing that was done. I purposely did that. So we're going to then try and do the same by trimming off that. How do we trim off that? So I'll go back to my part module. So if you go to the part module at the top end here, so there is this button which called extrude cut. So if we select extrude cut, it gives us the original geometry. So what we're going to do as part of the extrude cut here is we're going to kind of do something really very interesting. So I'm going to create, if I tick here and go there, so what I've used is that I've drawn a square in that window, another, you know, a rectangle or square in that window, and then draw another bigger square of any dimension. So what you notice here in this design is that I've got a tubular structure where the empty part of the tube represents the particle, the space that I want to preserve. So this almost like you're extruding, but you're extruding with an empty space, and that empty space will end up trimming off that, preserving what is in the content in there. So basically you draw the first circle, first square that fits in the region that you want to keep, and draw a bigger circle so that this space around it becomes what you're going to extrude. So you're going to use to come up, and then this becomes the final example, final result, showing me the matrices and the particles in their place. So then let's try and mesh. Okay, so if I select here, double click there, then I can seed. So it's recommending 1 as a seed side. I can start off with that, with a 1 seed side. So what I did, so I'll go through that again. So if you go to the top here, you click on seed. So it recommends a seed size. You can change it if you want, maybe 1.2, okay, or 0.8, but it's offering us 1. Usually the defaults are fine. So then you can assign mesh controls on this button. So what kind of meshing do you want to use in this case? So I'll select all the material, click done. So at the moment is the default is usually quad and quad dominated, which are likely to quadrilaterals. But because of the complex nature of this shape, we're going to use a triangular shape, and we're going to allow this meshing technique to be free. So I click OK. Now the next thing we need to then do is I'll look at assigning the element S4R. So this is where you assign what element you want to use for this simulation. So usually, because it's a continuum study, so I'll look for what the default is, a plane stress element, you know, linear, quadrilateral, so these things are all acceptable. And then finally, to show what the mesh shape is, so I click on that, and then I click yes. Okay, so that looks sort of a quasi okay-ish mesh. So let's look at the meshing algorithm, the mesh quality, or the mesh investigated mesh. So if I click on the eye at the top of the toolbar, so it's a querying tool, so it queries information. So I just look at the mesh and click done. So it gives me some history of what the meshes are. So for example, it says the total number of nodes in this model is 196. So if we zoom in, with 349 elements. This is a student version of ABAQUS that I'm using to demonstrate this, because I assume most students will probably have a student version. If you don't have a student version within your university, you have a bigger, a complete license, and that's fine. You can then don't worry about this. But let's say you're using a student version, in which case you're conservative in terms of how many meshing you're going to use. Clearly, this is something you can do. So the student version allow only 1,000 nodes in the model. So we currently have 196. So we're using about only 20% of the capacity of what we need. So let's try and refine the mesh. So let's see if we do 0.8. Okay. So delete the previous mesh. or maybe let's try something ambitious, 0.5. So half the original thing done. So if we mesh again, okay. So now if it said there are now 906 elements. So if we query the mesh again and then see what we have. Okay, so we still have 493 elements, 493 nodes. So if you look here, 493 nodes, so it's still okay. So let's try changing that. Maybe if we try 0.3, just to have as much element types as much mesh quality as possible. So click yes. Okay, so it says it's 2005. So we'll query the mesh again and see what we get. So now we are in trouble. It's 132. So if we try to run this simulation, it will not allow us. So we go back. So I'm going to try 4. Then delete the mesh, 0.4. Mesh the model again. Okay, query the mesh quality. So 774. Okay, so we got 774 elements, which means we will be fine if we go ahead and mesh this. So this is a good model. We have that setup, it's properly meshed. The sections are all in place. Aluminium section, silicon section. What are we going to do with this? I mean, okay, so the next thing is to try a step. So if I create a step, so I'm going to call this a loading step, and a static general analysis is fine. Okay, now what other things could we do? So we'll probably look for a history output. So what kind of history output am I going to use here? So so let's just leave that history output default associated with okay, so now let's forget history output for now and just generate the result that we want. Okay, so the next thing is to think about the boundary conditions. So I'm going to fix this and pull it from the front. Okay, so fix the back securely and pull it from the front. Okay, so if I look at this, so fixed back, and my loading step will be initial. So I'm going to change to displacement, boundary condition, so that I can control what I'm trying to do. And then at the back here, while pressing down shift control, I'll select the edge. Okay, so well, I just press down shift, so I select that edge. Okay, and click done. So that gives me the option I want to fix. So X is the one direction, Y is the two directions. So basically, let's fix it completely. Okay, and then let's apply a load. So tensile in the X. Okay, times X. But I'm going to make it, instead of a loading initial step, it's a loading step, because I want to apply the step. Continue. So we select the front end, press down shift again, select that front end, select this front end, and click done. Okay, so now I only want to apply the load in the X direction. So I'm going to apply maybe a 10% loading on this material, a 10% loading, or maybe we could try, so if we apply a 10% loading or 20% loading, so what would that be? So it's 10 meter long, so 20% loading will be 2. Okay, so we've got the loading applied, the structure is properly meshed. So the last thing is to just submit that job. So job, okay, maybe a alum sick, okay, tensile 1, tensile job 1. Okay, maybe simulation 1. So this is what we have, tensile deformation of simulation 1 with aluminium 6. So we created that job. Okay, so it gives us some information about setting up the job. We say okay, and then if we open that again, we can see, if we right click on that, you can then submit this job. You can do a data check just to make sure everything is fine. It's a good thing to do, but we normally will go and submit the job right away. So it's checking to make sure that there's no error in the setup of the job. At the end here, it's a file processor completed. Hopefully everything should be all right. Yeah, so it's completed successfully. So it's finished checking. Then we can, so once check is completed, then we can right click and submit. So that's, then click yes. so that it can then go ahead and run the model. And as it's running the model, it'll be giving you some information about what it's trying to do. If you're running the model and you want to monitor, let's say it's taking a long time, you want to monitor what is happening. So right click on the job again and look at the monitor option. So the monitor option gives you a window like this that tells you simulation, what's happening. If there are errors, you will see all that. But we're not going to worry about that for this. So this has finished running very quickly because it's a linear elastic result study. So look at the results. Okay, so right click on it and click on that. So it shows you typical simulation results. So if we animate it using this option, the second one here. Okay. Yeah, so it gives you an idea of how the simulation is going, so we can reduce the speed so that we can monitor things a bit more to see what's happening, how the stress is being transferred. Mainly, if you look at the end, most of the stress is being carried by the inclusions, and this is why nano-composites are brilliant, because all the stresses are being transferred mainly by the inclusions. The metrics sort of remain unloaded. This is a linear elastic simulation we're doing. So if we go back, I'm just going to change the metrics into something that can actually fail. Okay, so something that can actually fail. So let's go back and look at the results. So and see what we get. So this structure is taking a load of nearly 2,300 megapascal, 2,300 gigapascal, about 2,300. So it's quite a significant loading, and which is not ideal. There's no practical possibility of that. So we're going to change that, and we change the aluminium metrics. We know that aluminium will probably fail at a stress of 400 megapascal. So I'm going to change this aluminium, okay, by adding a plastic element to it. So I'm going to allow it to fail plastically. So in which case I'm going to introduce yield stress. So the yield stress of this aluminium is 400 e to the power 6, 400 megapascal. And plastic strain, it starts at a plastic strain of 0. It's always has to start from 0. So now that we've done that, I'm going to create another model, another simulation. So this time around, I'm going to call it Job Sim 2. Okay. So again, the same file name, alumsic tens simulation 2. Okay. So everything is there. So we click OK. Now we can run that model, submit it again. The difference is that this second simulation is now having a matrix model that is actually plastic. That is plastic that can actually fail plastically. Unlike the previous case that was taking ridiculously high loading because it didn't have the possibility of failing plastically. And clearly, because of the plastic deformation, it's taking longer to run, so we can monitor what's happening. So you could see it's running and it's showing you the progression. So it's moving, and then finally the time step. What you want to be looking at is the total time it takes. So how long the simulation is taking to run. So now let's look at the result. So if you look at the results for this second case, okay, you'll see some things, a slightly different behavior than the previous case. So the simulation is happening now, allowing some plastic evolution within the material. So if we change to that. So if we look at the end here, so there's von Mises stress. So we could look at some other quantities like the plastic strain built in within the material. So it gives you more insight into how the plastic stress is being developed. So the particles were elastic, so they didn't show any plasticity, but the matrix, which is aluminum in this case, is showing a dominant plasticity in the material. So they are failing plastically. So if we can run the animation, so it will give you an idea. So basically almost like a shear band, as the matrix begin to plastically deform, the shear band builds and travels through the material even to the end. So you've got the first one and then the second one, and you've got a different behavior. So this is a more realistic behavior of this metallic nano-composite than what we had before. So if you compare it with what we had before, so this case, obviously it doesn't, this is, the stresses here are too much, nearly to 23,000 megapascal, so which is not practical. So this is why you have to allow plastic deformation of the material, of the matrix. So, and in this plastic deformation, especially if you switch it to plastic strain, you get better behavior of what's really happening. So AC yield is a parameter that tells you the actively yielding elements, the AC yield, the actively yielding elements. So, and it shows, if you run the animation, it shows you when the first element that starts to yield and how it's built up in the material. So the inclusions, the particles never yield. What really yields is the material that are plastically deformed. So we go back to the plastic strain. So plastic strain is a useful quantity to use. And this is really all that we can do, you know, with this kind of simulation. It's what we can do. Of course, the next thing we can do is to try and do some analysis, some stress analysis based on getting some stress strain graph based on this. But this will be the subject for a different video. It's really useful.